Dear fellow coders, welcome to One Little Coder. This is day 17 of Kaggle's Machine Learning Challenge, and we are in the series of learning about machine learning explainability. In this video, I'm going to talk about partial dependency plot. What is partial dependency plot? How does it work? How do we implement it? And when do you want to use it? So that's what basically we are going to see. And this material is actually put together by Becker, who used to be with Kaggle. So this is not my own material. This is really a world-class material. And all I'm doing is taking you through what it has been already written and giving you some intuition about that from my experience as well. So let's get started with partial dependence plots. So if you had watched the previous video in this series, you know that we covered feature importance. We also called it permutation importance because we were doing permutation to identify which feature is most important. Now, how does partial dependence plot change from feature importances? Feature importance help you understand what are the variables that most affect your prediction. Like if you remember again, we had a chart that used to say, okay, these are the top 10 features that used to affect the prediction most. But what partial dependence plot would show you is how a feature actually affects a prediction. How much a feature actually affects, like how in the sense, for example, let's take an example. For example, if you are doing a housing price prediction problem and you know one of the columns that you have is square feet, let's say like the size of the house. Now feature importance would tell you where does square feet or the size of the house stand in the top 10 or top 20 important features. Maybe it is the most important feature. Maybe it is the least important feature. It might be in the second position or third position. That's what feature importance would tell you. Now what partial dependence plot would tell you is how that size. For example, if you have 1000 square feet, how much the prediction changes. If you have 1200 square feet, how much the prediction changes. If you have 3000 square feet, how much the prediction changes. So partial dependence plot would help you understand how this feature affects the prediction rather than just simply putting each feature against each other. So I hope this makes sense, but if you think like it doesn't make sense, going forward it will make sense to you. So now why do we need partial dependence plot? Just like we discussed, it is useful to answer some questions. For example, if you control all the features of houses, like if you're doing a house price prediction problem and you control all the features, like all your existing features, controlling in the sense you keep them same, you don't change anything. So if you control all the features of the house, can you measure the impact of longitude and latitude that have on housing prices? To say it in another language, you can simply try to find out if the house size stays the same, how much the price would differ for different area. Like for example, how much is the size if you are looking for a house in Bangalore? How much is this, for example, if the size is same, like 1200 square feet, what is the price of the house in Bangalore and what is the house price for the same house in Mumbai? So you keep all the features controlled, like you keep them static, you don't change them, but still you try to see how one particular feature would change the pricing prediction. So that's what partial dependence plot would help us understand. Another thing that it would help us understand is are the predicted differences. Like for example, if you're trying to predict something like medical related prediction, are the predicted health differences between two groups due to actually their diet, which could be one of the variables, or due to some other factor. So you might have 10 factors, you predicted something. Now, do you know the prediction that you made is actually due to the diet, which is one of the feature, or it could be related to something that you did not expect? So these are some questions that a partial dependence plot help us understand. So now to understand partial dependence plot could be understood in the same way that you understand coefficients of linear models like linear regression and logistic regression. If you are not familiar with linear regression and logistic regression, do not worry about it. We are going to slightly future into this video. We are going to take a decision tree example and then we'll look at how partial dependence plot would connect with the decision tree rules. So don't mind much about it. But the only thing that you have to understand is the way coefficients represent the positive and negative impact of a particular feature over prediction, the same way partial dependence plot help us understand. But the only thing is you cannot calculate coefficient for complex models. Like the typical black box models, the models that used to be called as black box are still called as black box. So for those models, it may not be easy or there is no way for you to get coefficient. So what do you do in that case? That's where partial dependence plot help you unravel like what is going on with the sophisticated or complex models like ensemble models. So let's see how it works. First of all, just like permutation importance, partial dependence plots are calculated after a model is fit. So if you remember permutation importance, we first fit the model and then we actually try to shuffle the column values, and then we calculated permutation importance. The same way, partial dependence plot, or I should say PDP, maybe PDP is easiest to call. So PDPs are calculated after a model is fit. So this doesn't happen before a model is fit. This happens only after a model is fit. So the model is fit on real data that has not been artificially manipulated in any way. So you actually fit the model and then you try to calculate PDP. So if you remember our soccer example, what did we try to figure out with the soccer example? So we were trying to predict man of the match, man of the game, with a lot of variables, like for example, how many shots they made, how many passes they made, how many goals they scored, how long a player traveled. So all these things we used to predict who could be the player of the match, whether a particular data point would be player of the game or not. So this is what we tried to figure out in the previous section. So now, if you take our partial dependency plot PDP, what we might start doing is, so we can start consider a single row. So in the feature importance world, we actually took an entire column, right? So that's what we did. We took an entire column, we shuffled them, and then we tried to do some prediction. In the PDP world, what we might do is, let's take one particular row. Okay, so that row, for example, it might represent that the team had a ball for 50% of time, they had made 100 passes, they had 10 shots, and they scored 1 goal. So this is like your single row. These are like columns, and you have some data filled in for this. Now what we might do is, we would take the model that we fit. So we have already built a model that would predict the man of the match or man of the game. So we already have this model. Okay, so now what we would do is, we would take this model, and then we would pick one variable, and then we would alter the value of this variable sequentially. For example, to give you like slightly specific example, so we are going to take this model. Let's say we have built a model and then we have this row. We're going to take this and then say the column that I'm going to pick is, let's say, how much time that the player or team had ball with them. Okay, so this is one of my column. Now what I might do is, exactly the data that is available there could be 40% of the time, or in this case 50% of the time. So now what we might do is, we might take this particular value and then we would iterate it from, let's say, 0% of time, 10% of time, 20% of time, 30% of the time, and we would make different predictions. So what we are trying to do is, we are trying to see how the prediction value changes for every value of this particular variable or feature. So let me repeat it again. So if you think of X and Y axis, we are going to take one variable that we have used to build the model, and we have predictions. So your x-axis is the axis where you have taken that variable, and your y-axis is the axis where change in prediction, how much prediction changes or prediction. So now what you're going to do with your x-axis is, you're going to change the value of that variable that you have taken. In our case, what we have taken how much time the team or the player had ball with them. So our current value is 50%, but what we might start doing is, we might iterate it from some lower value to an upper value. So we might start with 0%, 10%, 20%, 30%, and for every value we would plot what is the prediction. Okay, plot it, and then we would go till probably, like, let's say 90% or 100%. And now at the end of this, we have a series of data points that we can actually plot, like I just showed, that would tell us how that one particular variable, change of values in that particular variable changes the prediction outcome. So we took one single row and then we changed one particular value, one particular column feature, and then we changed the value of the column to a series of values, and then we made predictions every time, and then we are going to see how that predictions have changed. And we are going to repeat this like for multiple rows. Now I just said it for one row, but we are going to do the same thing like for different multiple rows from the original data set, and we are going to take the average of it and plot it in the chart, just like we did. And that is what is going to give us the partial dependence plot. So basically how much the prediction is dependent on the variable or the change of the variable. If a value of a variable changes, how much the prediction changes, and that's what we are going to see with partial dependence plot, PDP. Now let's look at the program code. We are not going to focus on the model building exercise, but just to quickly say, NumPy, we are going to use it for a random number creation or anything that is required, like random split, and pandas for data frame manipulation, train and split for model validation, random forest classifier because we are actually trying to predict man of the match, which is a Boolean value, true or false. We are using a classifier, and again, to look at a simple model, we are looking at a decision tree classifier as well. So we have imported the classes for two models. Now we have imported the data set, we have extracted the target value, we have extracted all the numeric variables where we have got the feature names, and then we have assigned it to the X object, which is what we usually denote our the features that we are going to use for model building. And then we are going to do train and test split, and then we have actually built a model decision tree classifier with random state 0, maximum depth, like number of depth that we want to go, minimum sample split 5, and then we have also fit, like we have defined and fit. You can see the two steps we have done it in one single step: define the model and then fit the model. So now this tree underscore model is an object which is a fit model. Now what we are going to do is we are going to visualize the model. We are going to see how the decision tree, one of the biggest advantages of decision tree is how easy is it for you to visualize, and you can convert into rules. For example, it is possible that your business or your stakeholder might ask you to give the machine learning prediction in terms of rules, which could be used for let's say marketing campaign, the example that we were seeing, or which could be used to, for example, if you're talking about credit score model, now you can use these rules to say, okay, what kind of person would default. Or if you have ever seen Moneyball movie, you might see that these kind of rules could be used for player scouting as well. Like if you are going to pick a player in a draft, you might want to know like what kind of player you want. So maybe your decision tree will give you an idea about, okay, this is the type of player I want in my team for my team to win. So you can do all these kind of things. So decision tree is extremely helpful in visualizing your predictions in the model. Okay, for that we are going to use GraphViz. GraphViz is an external library that we are going to use to visualize the decision tree. So import GraphViz, and then you have the model tree model, and then you just have to export GraphViz, the tree model, and then you actually see the tree. So the way you read this chart, so you can see the decision tree, the way you read this chart is anything that goes in the left hand side, after the split is true. Anything that goes in the right hand side after the split is false. And when you look at this decision tree, something that is at a node level like this, you can see at the top, you would see the rule based on which the split is happening. Anytime you look at the leaf, the left hand side is the false value, the right hand side is the true value. So the count of false values, the count of true values respectively. So you can see in this case, false, 15 false means the majority says that if somebody follows this rule, they may not win the man of the match. And in this case, you can see 0 false, 3 true, which means if somebody follows this structure, you can see that there is a chance for them to win man of the match. And if you see this, for an example, this leaf, you can say, okay, 23 is for true, so there is a very high chance for somebody to win the man of the match if somebody follows this track. So you actually traverse back, and then you see, for example, okay, if somebody had scored goals less than 0.5, if it is false, which means they have scored goals minimum, at least like they have scored some goal, then you come here, then you look at this thing, and then you say this is true and this is false, which means their number of items is more than 24. Okay, then you come here, then you have already hit the, if their number of items is less than 24, then you would go here. If their number of items is more than 24, then it means you say that they may not be man of the match. Now when you come here again, you do this calculation rule, you do a split, then there is a calculation rule, then you do a split, then there is a calculation, and then finally you decide this thing. So basically your leaf tells you the count of true and false and the true value. Your top node, wherever you see the node, it would give you the rule based on which the split is happening. So that's how you basically read this decision tree. And like I said before, decision tree is really helpful in visualizing what is happening in the model and also extracting rules. Now that we have learned how to read a decision tree, and we also have exported the decision tree, which is something we are going to use in near future, let's make a partial dependency plot, dependence plot, PDP. Okay, for that we are going to use a library called PDPBox. So you can go to their documentation and understand how to install PDP. So you can actually, this is just one pip away. From PDPBox we are importing PDP, get dataset, and info plot. Once we import all these things, you can see that pdp.pdp underscore isolate, the first argument is your tree model, whatever the model that you built, and the data set against which we are going to do this calculation, list of all the features that we use to build the model, and the exact feature for which we want to measure the partial dependency. Okay, so the model and then the feature for which we want to measure the partial dependency, like how the prediction value changes. In our case, in this case, we are going to use goals scored, number of goals scored, as the feature for which we want to see how much prediction changes. So after we build this, then we are going to simply say pdp.pdp underscore plot, and inside this we are going to say pdp underscore goals against goals scored, and we can show the plot. When we show the plot, you can see that when you look at your x-axis, that is where your goals scored, the number of goals scored, how we iteratively change the value to see how the prediction changes. So y-axis shows the prediction change, and x-axis shows how we iteratively change the value and their respective y value. Now if you look at this plot, what would be your first thought? Like just think about it. And if you are wondering what is this thick line, like the solid line, and what is this light shaded area, the thick line is the actual value, and then the shaded line is how much the confidence, like level of confidence is. So you can see the broader the confidence is, which means it's not the prediction might change a lot. So if you remember, like we already said that we iterate through for multiple rows, right? This is not only one row. We are going to iterate, we are going to repeat this experiment for multiple rows. So how much that value changes is what this blue shaded area, and the solid line is exactly what that average value is. So now when you look at this chart, just think for a second, and then like guess what does it show you. Okay, so if you have thought about it, so let me say, when you look at this chart, you know that when somebody does not have any goal scored, so then there is no impact in prediction, like there is no impact in getting man of the match. But when you see this, when somebody scores a goal that is slightly greater than 0.5 or closer to 1 goal, then the chance of them getting man of the match actually increases a lot. But also there is an important thing that you might notice is after that it becomes flat. You can see that. And so what this chart tells us is, okay, if you want somebody to become man of the match, then they should score at least 1 goal, but after that how many goals that they score doesn't matter as much as scoring the first goal. That's what we see. And the reason why you would see a very chart like which has one rule is because you used a single decision tree. The decision boundary that you get from a decision tree is very stepwise. So this is like a stepwise chart. Okay, so because you the reason why you got a stepwise chart is because you use a single decision tree who builds a decision boundary which is also stepwise. So if you go back to this, for example, this is a point, right, inflection point, and you can see the same here, 0.5, and then whenever something is greater than 0.5, you can see how it increases chance. Whenever something is less than 0.5, you can see the values falls as 24, which means the chance of somebody actually getting a man of the match reduces a lot. Like the false is 23 and then the true is 0. So that's what this is. Let's look at a different column. And in this case, let's look at a column value called distance covered. So you know that we have given distance covered as a column, the feature to plot, and you can see that is a value that we passed here. So here we passed goal score, here we passed distance covered here. Okay, now that we have done this, when you look at this chart again, it's another stepwise chart, and what do you see? You can see that when the distance covered is less than 100, there is no impact. But when it crosses 100 or something around that, you can see it again becomes flat, but the chance increase. Now let's go back and see where distance covered is. Distance covered is this, and when you see this, okay, when the distance covered is less than 1.5, then your chance, like true, when it is true, then your chance of becoming the man of the match actually is very less. That's why if you see this see somewhere around here, you would see like 3 false values. But when the chance of distance covered is more than 101, then you can see the chance increases, and that's what you would see from this partial dependence plot as well. So it's always a good exercise for you to go back to your decision tree and then compare. But again, if you actually think about reality, can reality be this simple? Can reality be like a stepwise chart where you just say, oh, this is one route, and then this is like the rest of the things that do not matter? The reason you see a plot or chart like this is because we used a very simple model. But what if we change the model? Instead of using a random forest, which is instead of using a single decision tree, what if we use a random forest that will be like a lot of decision trees? How our predictions might change, or how our partial dependence plot might change. So we have already imported the random forest classifier here. So what we are going to do now is we are going to simply build a random forest model and also fit it. And it's a very baseline model. You can see like we have not used any hyperparameters. Once we do that, now if we build the same partial dependency plot for distance covered, it's the same partial dependence plot for distance covered. You can see how the chart has changed from being a stepwise. You can actually see there is a smooth shape, like there is a curvy shape here. And then what it shows is when the moment you score more than 100, when you cover the distance more than 100, your probability of winning man of the match increases. But after a point, like if you see somewhere here, the chances start coming down. Like you can see the chances start coming down, and that's what this new model is telling us. Like initially there is no chance. The chance increases slowly, chance goes to peak, and after this it starts coming down, So basically, like even if you cover longer distance, it says like your chance of man of the match might go down if you start covering more distance after a point. Okay, so now there are a couple of things that you need to notice. For it to take exactly like this, you need to know how much your data, like if your data is small, there is a very high chance that even this plot might be a biased plot, in the sense like this plot might not give you the true picture of what is happening. But again, it is like you know, like there are a lot of factors, right? A simple model may not overfit that much, your random forest might be overfitting. So there are a lot of things that you might have to deal with. But again, the bottom line is always your curved smooth PDP is better than your stepwise PDP, because this is more plausible, like you can believe this more. Okay, so now that we have learned how to look at how to build a partial dependence plot, how to look at a partial dependence plot, how to connect it back to a decision tree, and then how to interpret them. So let's look at 2D partial dependence plot. Now you might ask me, what is 2D partial dependence plot? Isn't it already 2D? Okay, what is 2D partial dependence plot is, here what we actually did is we had a single feature and then we had prediction. What if we can compare two features? Instead of using a single feature, what if we can use two features? And again, that is again a very good way of us to compare two features. So how two features interact with respect to prediction. So now if you look at this, the features that we want to plot is goal scored and distance covered. Instead of using one feature, unlike before, we are going to use two features to create a partial dependence plot, and that's what we are calling as 2D partial dependence plot. That would give you something like a heat map like this, like the chart like this. So basically the syntax would stay same, like PDP underscore interact, and you give the features to plot, and then when you plot it, you can give the plot type, what type of plot. This is like a contour plot, or what kind of plot you want. You can definitely go here in the documentation and then look for what kind of plot you want, what are the attributes that you have. But if you look at this plot, you can basically again connect it back to your decision tree. What you can connect it back to your decision tree? A decision tree said, like when you increase goals more than 0.5, then your prediction value, you know, the chance of your prediction increases. That's what you would see. But again, after a point, it doesn't matter how many goals you, this is based on decision tree. I'm not saying that, you know, this is how a true decision boundary or like a complicated model would have. But if you want to connect it back to decision tree, you can actually see that when your value increases more than 0.5, then your chance increases. But after it hits 1.0, then the chance doesn't change much, like it stays same. And on the y-axis, if you see the distance covered, when the distance covered increases, how you can see the value like changes here. So like this is like your sweet spot, and you can see how these values, you know, interact with each other. Again, one of the things that you should do is look at this chart and then also see if you can connect it back. For example, we see the highest prediction when a team scores 1 and also they run a distance of close to 100. Like this is our peak sweet spot here. If you can see, this is our sweet spot where the highest prediction value that we have got. So you can just compare this with your other columns and then see how two features interact. Again, this has huge like you can use this for business impact. For example, if you're designing a marketing campaign, you're not going to simply use one feature, but you want to find a set of attributes for which you want to target a like group of people, or like the Moneyball example that I gave you. So you don't want to pick a player based on one attribute, but you want to pick a player based on multiple attributes. So understanding what are those attributes that might give your team currently based on your current team composition might help you pick the right player that you want. So again, 1D partial dependence plot, which is like this line chart, the 2D partial dependence plot, which is like your heat map. These two are really helpful for you to understand how a particular feature or a set of features might impact the prediction or do impact prediction, and how also these two features interact with each other. And you can always go back to your decision tree and then compare it with this when you have a decision tree, of course, right? When the whole point that we are discussing this is when you do not have a decision tree, also when you have something like random forest, XGBoost, light GBM, or all these ensemble models, how you can still make sense of it, how you can break that black box and then get some insight out of it to understand how these features impact the prediction, and give some insights to your business. So that's what partial dependence plot is. So in this video, we learned about what is partial dependence plot, how it basically works. We looked at the code example. We also learned about how to interpret that, how to understand that, how to translate into a business point, like English point. And then we also learned about 2D partial dependence plot. And finally, you have to start doing the exercise. When you click this link, it will take you to the exercise. I'm not going to do the exercise because I don't want to ruin your experience of doing the exercise. But if you want certification for machine learning explainability from Kaggle, again, like it's not about just certification, right? Even if you want to truly learn or understand what you have learned, you have to go to the exercise. Basically, you can simply copy the code here and then you can start just filling in there and then do the exercise. It's not a big deal, but it is for your own learning. So thanks so much for Kaggle Learn for putting together this material, and Dan Becker for putting together this material. If you have any questions, please let me know in the comment section. Otherwise, in the next video, we're going to learn about SHAP. See you in the next video.